Welcome to this podcast entitled Applications in Computational Chemistry. The guiding question for this podcast is one of the central questions in the Introduction to Computational Chemistry course, that being, what is the role and the purpose of computational chemistry? What does computational chemistry allow us to do that cannot be done using traditional or wet chemistry? And we'll be giving you examples of some of the things that we can do in computational chemistry that cannot be done in traditional chemistry, and examples of things that can be done experimentally as well. So you'll see a little bit of both in this podcast. All right, under applications, there are a number of things that we can do in computational chemistry. And by the way, the term application here does not refer to a specific piece of software. For example, we might say that Microsoft Office is a computer application. We're not using that terminology the same way. We're using application to refer to a specific type of calculation that can be done. So we'll start off with the first one, that being geometry optimization. And I have the phrase pre-calculation here because, as you've seen in the course so far, you should understand by now that before you do a calculation that it has some meaning to it, you should typically always optimize your molecule first, and we'll talk a little bit more about that in this podcast. It is, however, the case that sometimes the application you're trying to do is simply trying to get the molecule to optimize. So you will see entire journal articles where the entire article is simply talking about how they got some particularly challenging molecule to undergo a geometry optimization. The primary application that we do in computational chemistry is what's known as electronic structure determinations, and the root word of electronic is electron. So 99% of the time in computational chemistry, what you're really looking to do is try to say, can I determine what the electrons are doing in an atom or in a molecule? Can I determine where they are? Can I determine the probability that they're here versus there? And you saw a little bit of that in the article on charge distribution in water. So what I was looking for, what they were looking for in that particular article was, where are the electrons, and specifically, how is the charge distributed over, in that example, the water molecule? So how many of the electrons are sort of hanging around the oxygen, how many of the electrons are hanging around the two hydrogens? So being able to determine the electronic or electron structure of an atom or a molecule is really sort of the fundamental thing that we do in computational chemistry. Okay. Once we're able to do that, when we're able to determine the electronic structure, then we can do a variety of other things, such as frequency calculations. And you've had a chance to do some frequency calculations. You've done them on water. So you have a little bit of experience with frequency calculations. We can also do what's known as a transition structure in computational chemistry. And this is one of the more complicated things that we do in computational chemistry, and we'll talk to that in another couple slides or so. In medicinal chemistry, for those of you who are taking medicinal chemistry, we'll be doing a lot of protein calculations, otherwise known as protein docking or protein ligand docking. That's where you take a molecular model of a protein and a molecular model of some drug. We call it a ligand. And what you try to do is to see whether or not these two molecules, the protein and the ligand, will actually interact with each other and cause something to happen. And that's called protein docking or protein ligand docking. And that's primarily done in courses or in applications such as drug design chemistry. We'll be doing a fair amount with what's called a potential energy surface, otherwise known as a PES. And yes, it is also called a potential energy scan. Typically, we use the term potential energy scan to mean the process, and we use the potential energy surface to mean the product. So if I say I'm going to do a potential energy scan, that means I'm going to do something. If I say here's a picture of a potential energy surface, that's the result that I got from doing the potential energy scan. Unfortunately, scan and surface both start with an S, so you'll see the term PES used interchangeably, and it means both the process of determining the potential energy and the actual product that results from that. In kinetics or in chemical reactions, we can measure the rate constant, so we can figure out how long does it take for a particular reaction to occur. Does it go fast? Does it go slow? And all of that is a branch of chemistry known as kinetics. So computationally, we can determine rate constants for chemical reactions, which is, by the way, very difficult to do experimentally. Okay? So that's one of the things that we can do pretty well computationally. We can also do what's known as thermodynamic calculations, basically looking at some of the various enthalpies and entropies and heats of formation. Some of those terminologies you may be familiar with, some of them you may not. And if you are not familiar with them, we'll give you a little crash course on thermodynamics when we get to that particular part of the course. And lastly, we can do spectroscopy, and some examples of that are infrared spectroscopy, UV or ultraviolet visible spectroscopy, and NMR, which is nuclear magnetic resonance spectroscopy. And we should have a chance to do a little bit of spectroscopy towards the end of the course. And this is a really important area in computational chemistry because the equipment needed to do experimental IR, UV, vis, and NMR is pretty hard to use and pretty expensive. So being able to do some of this computationally is a big plus. And this graphic you've seen before, these are the atomic charges on the oxygen atom in a water molecule. And again, that all talks to this thing called electronic structure determinations. Okay, I'm going to go through a number of these individually. We'll do them pretty quickly. The goal of this podcast is just to give you a general idea of what these different applications are. And needless to say, during the remainder of the course, we'll be spending considerable time doing each of these types of applications, each of these types of calculations, so you're a little bit more familiar with what they are and how to do them and what the results mean. So in geometry optimization, that's the process of determining an energy minima, or the low point. Okay? And what we do in a geometry optimization is we adjust the bond angles and the bond lengths that give the lowest possible energy value. And you should remember that a lower energy value is more stable. It's an iterative process, meaning it's a process that goes round and around until we get to a right answer. And it's an iterative process that starts with a guess geometry and then ends up with an optimized geometry. And you might recall the Newton's method spreadsheet where you started out with a guess for the value of x. You iterated it over some number of cycles until the computer said, I think I have the right answer, and it reported the answer as being a 2 for the function x squared minus 4. Same thing here. In geometry optimization, you start with your initial guess geometry, you build your molecule, and that's going to be your guess, and then you tell it to optimize, and hopefully it will converge and result in a optimized geometry that you now can use for further calculations and computational experiments. And a successful optimization only guarantees a local minima, not a global minima. So you've seen this chart before where what I'm plotting here is the energy as I change the shape and structure of the molecule. And you notice there it is possible when I do a geometry optimization to find a local minima. What I really want to find is the global minima, and that's harder than it looks. So if you're not sure whether you have a local or global minima, what you would do is you would repeat your optimization a number of times until you're pretty sure that you think you have a global minima. And we won't spend too much time on these in this course, but just keep in mind that when you do a geometry optimization, just because it tells you it found something doesn't necessarily mean it's the exactly best answer. Okay, single point energies are the prediction of the energy and related properties of a molecule at a specific geometry, meaning at a specific bond length, bond angle, and dihedral angles if you have those. So a single point energy says, okay, I know exactly what my geometry is, and I want to know the energy of the molecule when it has this structure. So that's called a single point energy. And it's used to obtain basic information about a molecule. It's used to check the reasonableness of a geometry, and you'll get to spend a little time trying to understand what the word reasonable means when we're talking about a geometry. And we use it if I have an optimized geometry. I can use this method to compute a very accurate energy for an optimized molecule. Okay? And on the server, this is known as a molecular energy calculation. So when you go to, say, MOPAC, and you go to the calculation pull-down menu, you'll see the word molecular energy, and that is also a single point energy. So those two terms are often used interchangeably. Okay, frequency calculations, you have some experience with those. You know that all molecules vibrate. They vibrate at specific frequencies depending on the molecule. And the measurement of these frequencies allows us to identify a molecule. So it's sort of like a fingerprint. I can get a infrared or IR frequency spectra, and I can tell you by looking at that spectra exactly what the molecule is. Again, so we can do an infrared or IR spectra. All molecules have a specific number and type of vibrations. You saw the 3n-6 rule a couple times already. And you know that there are different types of frequencies, stretching, bending, and here's a chart of vibrational modes. And again, you've seen this chart a couple times with stretching and bending modes and the 2 different types of stretching and the 4 different types of bending vibrational modes. You're going to see these a lot more, so it'll be important for you to be able to recognize these vibrational modes and use that information to say something intelligent about the molecule. The biggest thing we're going to do in this course, and this is one of the hardest areas for beginning computational chemists to understand, is what's known as a molecular orbital. And these are representations of where the electrons reside. And there are different types of molecular orbitals. By the way, if you look at the graphic here over on the right-hand side, you see these little sort of like balloons. Some of them are blue, some of them are red, and you will become very skilled at looking at these red and blue balloons and being able to say something intelligent about what they mean and what implication that has for the structure and behavior of the molecule. The molecular orbitals that we're particularly interested in are what's known as frontier orbitals, and we'll be talking to you about a theory called FMO, or Frontier Molecular Orbital Theory, for which Roald Hoffmann up in Cornell University won the Nobel Prize. And everybody gets a big chuckle out of this, but there are 2 types of frontier orbitals. The first one is called HOMO, and that refers to the highest occupied molecular orbital. Okay, so that's one of the 2 frontier orbitals. The other one is known as the LUMO, and that is the lowest unoccupied molecular orbital. And it will be critically important for you to be able to identify which molecular orbital is the HOMO, which one is the LUMO, and be able to say many intelligent things about what that means in terms of how that molecule is going to behave in a reaction or in some other environment. Most chemical reactions, as you're going to learn, happen at the HOMO or LUMO. So as I just mentioned, being able to tell me where the HOMO and LUMO are is going to be really important, because that's the only way you're going to be able to say, yes, this chemical will react with this other chemical, and that's an important part of what you're going to learn in this course. Potential energy scans or potential energy surfaces. It's also known as a coordinate scan. It'd be nice if we had one name for these things, but we don't. When you do these on the CompChem server, the option it gives you on the menu is a coordinate scan, and you have to sort of in your head understand that that's a potential energy scan. And the goal here is to find the most optimal geometry, bond length, bond angle, etc., over a range of values. So the graphic here is going to show what's the most optimal bond angle for this particular molecule. So I did a coordinate scan or a potential energy scan on this particular molecule, and what I'm adjusting on the x-axis is the bond angle. Okay, so I've changed the bond angle. I started the bond angle at 90 degrees. I went to 95, then 100, 105, 110, all the way up to 130. And what you should notice on the chart here is that the coordinate scan is telling me the most optimal bond angle for this particular molecule is somewhere about 107 and 108 degrees. And this is indeed water, so around 107-ish or so. Okay, so you'll be doing potential energy scans and on a variety of different molecules. So the process again is called a potential energy scan. The graphic that you see on the right-hand side of this slide, that's the potential energy surface. Okay, so that's the product. That's the thing that results from what you did. Okay, And there was another one. Was in there? Okay, there we go. Here's a transition state. This may be a familiar looking graphic to some of you. What this graph is showing is that I have reactants on the left-hand side, and I'm going to allow those reactants to undergo a chemical reaction, and what's going to occur is that I'm going to form some products on the other end. So I'm going to take two chemicals, I'm going to put them in a pot together, they're going to react, and some new chemicals or products are going to emerge on the other side. The graph here is showing you the energy curve as I move from reactants to products, and I'll be able to measure things like the activation energy or the activation barrier. I'll be able to measure things like delta G. And again, these are terms that some of you may have experienced before and some of you may have not. And if you have not, we'll talk about the chemistry of this when we get to that particular section in the course. So don't worry about it too much yet. Thermodynamics is we're interested in the amount of energy in the molecule, and what you see on the right-hand side are a variety of different types of energies. We typically measure these things as heat, and some terms you may know, some terms you may not know are things like enthalpy or delta H. So you might have heard of delta H of formation or delta H of reaction, delta H of sublimation. If you're familiar with those, that's great. If not, we'll take care of it when we get to that unit. Some of you may have encountered the term entropy or delta S. Some of you may know the formula delta G equals delta H minus T delta S, where T is temperature. And again, if you don't know any of these things or don't remember them, we'll introduce you to them or review them with you when we get to the thermodynamics section of the course. If you have any questions, we'll talk about them during the video conference, and I'll look forward to seeing you at that time, and we'll see you. Have a good day.